analytical growth methods. So compare data using experimental method, using analytical, using ODE, and using integral, and we would graph those. The real challenge of this project was using ODE itself. That was hard. So on to the program. So here at the beginning, you have your housekeeping commands: clear CLC, close all, and here is where the user would input the values of n in a vector and the values of t in a vector. And if these vectors do not match, the user would be asked to enter the vectors again until they're the same dimensions. That's what this while loop does here. If it doesn't, it sends them back until they finally do it. Here is the constant. A is a constant at 5.0, B is a constant at 2, and W naught is a constant at 0.5. And this is the span because the time cannot be, it has to be from 0 to 20. And here we created an empty vector of 0 with the length of n being 6, so with the length from 1 to 6, and this for loop goes through ODE 45 and it gets values. It solves the differential equation, this differential equation that we were given that's here. So it solves this differential equation and gives values for time from t1 to, and then also gives w, which is the weight at the end of that. And this for loop checks if the values of w are less than 10 or barely approaching 10, so not over 10, then it tells the corresponding t values at that w that is not 10, and that t value is stored in t naught t, and that w value is stored in w. And so that's the ODE 45 part. We used a function handle instead of making a function all on itself, which made things a lot easier. My computer's about to die, so let me put my charger on real quick. It would suck if the video just stopped and my computer dies. Okay, my computer's charging now. Okay, so what was I? Oh, so this function handle is used instead of calling a function, creating a function and calling it. It just saves a lot of time. Here is created t2, t of 2, which is just a vector of zeros, which stores integral values that are gotten from the differential equations, and this integral integrates from w naught being 0.5 to 10, which is the maximum. So this is just a scale we just created because it can't be more than 0.6 to 7. So we just wanted to put empty. We wanted to create a zero vector to store this right here. This being the analytical method, and we had to rewrite the equation actually, and this equation is rewritten. It was a lot of math, but we finally got through it. And this equation is rewritten this way with absolute values, and the t3 of I, which is in every which is indexing the i's, so which goes back and replaces a 0 with the value that's made by this equation, so there should be about 6 of them from t. Now here we are going to print out the fprintf statement. So this fprintf statement, the fprintf statement prints out ODE in the feeding value, so it's going to print out what we have here. This is what it should print out, and the for loop that we created actually prints out those values. Instead of us making an fprintf for each of these values, we did an f for loop that goes and makes and puts that value. It was pretty specific formatting, but it puts the values for n and t1, which t1 is the corresponding time when the weight is less than 10 in each iteration in the ODE, and then n is the user entered value. So, and we created another for loop to print out the integral part, which is here. It's going to print out, and it does the same thing. Instead of doing each fprintf, we did a for loop that prints out all of them at the same time. And here is the plotting. So we plotted our graph to look exactly like these. We plotted looks exactly like that. Hopefully, yeah, it does. Looks exactly like that. And there's all the plotting formats. This part, it plots t versus n, black circles, and hold on makes, so we're going to plot this other plot on the same figure 1, so we won't have to make new plots. And these are just the legend. The legend automatically does the best fit, so we didn't have to put the coordinates for where it was going to fit. And the Y label is the time it takes the fish to grow to 10 pounds, and that's in weeks. And the X label is the feeding efficiency. And the title is how long it takes for the fish to grow to 10 pounds at different feeding efficiencies. Now figure 2 plots the inverse, the reciprocal function, and we use polyfit. We did a regular polyfit with mx plus b, but we did the inverse of that to plot that, and we plotted the reciprocal versus just x, which is just a range, I guess. It was just made up. And here, this is where the plot of the cubic method is used, and we used, and it's from 0.6 to 0, of course, like the text says it should be. And we use interp1, and we plotted that against x1 being a line space from 0.6 to 0.7. And so this is the cubic method. I had to actually look up the syntax. We weren't taught this in class at all. And it's going to be a black line width of 3. And the Y label is time it takes the fish to grow to 10 pounds, and the X label is the feeding efficiency. And the reciprocal and cubic method, that's the title, and the legend also describes the properties that are being done. So now let's go through and run this program. I'm going to do run all. Well, let's not do that. Let's just run this section. I am not in this right folder. I'm not in the right folder right now, but I guess I could go to that folder. Let's see. No, not that. Oh man, this is gonna take like a lifetime. Oh, okay. I'm going to click this. And then, okay, it doesn't matter. I could be in the right folder or not, but I'm going to run this section and then input the vector values. Input the all the vector values. This is for t. I mean, this is for n, of course. And then this is input all the vector values for t, which is time. So it should be exactly like this. Okay, so this is the fprintf statement. The formatted output, which looks very similar to this, should be same. These values are originally not just 7, 4, and 3, 3, 2. They're actually like 6.8, but this is formatted, did only 2 decimal places, so it just rounded up to 7, 3, 4, 7, 4, 3, 3, 2. And this is as the exact same, the feeding efficiency, the user entered feeding efficiency, and this is using integration. This is using ODE, and this is the output use. So this is using ODE, and this is output using integration, and these values are very similar to that. So it goes down, as you can see. And now the graphs, where do they go? Okay, so these are the figures. Figure 1, and it's the time it takes the fish to grow to 10 pounds versus the feeding efficiency. And this graph is which is the cubic method and the reciprocal, the time it takes to grow to 10 pounds, and the feeding efficiency as well. And that's the printed out legend. And this has a legend as well that was formatted. So this red line is the analytical method that we plotted. This dashed line is the integral, and this dashed line and this green line is using ODE. And on this red line is a reciprocal function, and this is actually the cubic method. This is where those little points come from. Yeah, that should be it. So yeah, that's our program right there. There's not much to it. It looks good. Hope it looks good. It looks good to everyone. And yeah, thank you very much.